Hey everyone, hope you're doing well. So in this video, I'm going to talk about Markov chain attribution modeling. This, by the way, is the second installment in my series on GA4 BigQuery attribution modeling. The whole purpose, the whole motivation behind this series, by the way, and including this video, of course, is that we really need custom attribution modeling. I feel, and I think a lot of marketers might have as well felt that, and other marketing analysts. So, yeah, I mean, the traditional attribution models that we are all familiar with, that we have encountered in the different analytics tools, and sometimes within the ad platforms themselves, are last touch and first touch. Then there have been a few others over the years, like time decay and linear. I don't know, some of those are getting phased away, or already sort of phased out. So the point is that there's been a limitation. The options have been very limited when it came to attribution models, because if you think about it, take a couple of steps back. Attribution modeling is the mathematical concept, or the mathematical idea that you are using to make sense of the customer journey data that you have. So first things first, you need a customer journey data set. This I've shown how to arrive at that in my previous video. Please have a look at that. Once you have that, then you can move ahead with attribution modeling. So if you want to do a custom attribution modeling which is more mathematically sound and robust, Markov chain is a good idea to sort of adopt as an approach. So this is a probabilistic approach, as it mentions here, and that captures how customers navigate through different marketing channels. Okay, and the idea is to try and assign as fair a credit as possible based on the removal effects. So that is the sort of overall idea. um right, so I'll just try to zoom in for you guys if that helps. Yeah. So yeah, I mean, by the way, this document will be shared with you, and but yeah, just follow along for now, please. So what's a Markov chain? A Markov chain is a stochastic model. Okay, so that's kind of like saying probabilistic. So it's a stochastic model that describes a sequence of possible events where the next state depends only on the current state, not the sequence of events that preceded it. This is very important. And the state here, by the way, will see that each channel is a state. Okay, so each channel, like Google or Facebook or email or direct or whatever, organic, social, these are called states in the Markov chain regime. Now, the movement from one state to another is what concerns us, and finally to the conversion event. Now, what it means is that the dependence is only on the previous state. For a current state, or for the next state, the dependence is only on the previous state. This is the basis of the Markov chain, and without this, Markov chains don't work. So you can understand there is an assumption, and this is also a limitation in a sense. All right, but we're going to come to the pros and cons later. Now, there's a conversion path. We know about the conversion path, right? This is very familiar. This must be very, very familiar to you already. And this is called a sequence of states, because these are different states. Remember, each of these channels. The conversion is an absorbing state, because that kind of closes the thing, right? So that is that marks the customer exiting the chain. So how it works is a step-by-step breakdown here. Like, first of all, preparing the path data. This I've already mentioned. You need to have this kind of a data where you have the different channels, and their sequential flow. Now, how do you build something called a transition matrix? So that's the next step in this process. So you have to build the transition matrix, which basically is based on the calculation of probabilities of moving from one channel to another. So that is where you look into the percentage of users that move from one channel to another. So from email, you have, suppose, 60% of users going to direct, 40% going to Facebook. Right, we'll come to the visual part just in a second. We can have a visual representation of this, and this helps us calculate what's the transition probability matrix. Transition from one state, meaning one channel, to another, remember. So those are the terminologies. Then you finally compute what's called the removal effect. This is the ultimate agenda of this entire attribution modeling, because the removal effect means that if you remove a channel from the path, how much impact it is having on the overall probability of a conversion. And so if that impact is a lot, like, the extent of that impact gives you the extent of attribution credit, the credit that you want to assign as a form of attribution to that particular channel. So that's the whole concept behind it. Is it good, is it bad? We can talk about, we can weigh the pros and cons a lot, but yeah. And then you can finally assign attribution credits. So higher the drop in conversions upon removal, higher the attribution credit, like I just said. And the sum of all channel scores, by the way, equals 100%. So why Markov chains? It can capture multi-touch journeys, has indirect influence, as we'll see in a moment what that means. Provides fairer and more data-driven attribution. This is, in comparison to your traditional models like first touch and last touch. And then you have easy to visualization with graphs. That's definitely easy to visualize. That's definitely a plus point. There's no doubt. We'll just see in a moment. And it's, it can be considered better for foundation for budget allocation. These are just like some advantages that you may say, but yeah, these are things which can be disputed. We'll come to those things later. For now, just understand this as a method. You can consider this. And by the way, this is used in a lot of marketing measurement approaches, in multi-touch attribution, but also in marketing mix modeling. So for instance, in Google's Meridian, MCMC, which is a version of this approach, an extended version, which incorporates also Monte Carlo methods. That is part of, that is used for what's called a posterior sampling. I've actually talked about that in a previous video to a certain extent, so you can go and have a look at that. I'll probably drop that in the description as well. So this is, for instance, a visualization of this approach, and you'll see what is given here is C1, C2, C3 are different channels. So the user is starting at some point, and then it can either go to so either go to channel 1 or channel 2, and then from there it has, there's a possibility of going to channel 3, and there is a possibility finally of converting or not converting. So of course, it's a simplified version. You can understand that in reality the users can probably go through multiple channels, much more than just 3. So here's the scenario. So 50% probability of going to channel 1, 50% probability of going to channel 2, 100% probability, which means that there's a guarantee that if it goes to C2, it's going to go to C3, 50% probability of going from C1 to not purchasing, and a 40% probability, a 40-60 split between purchasing and not purchasing after it reaches channel 3. So this is a simplified version, right, where you have 3 channels and a few probabilities interlinking each other. So these ones, this 50, this 100, 40, 60, all these are called the transition probabilities. So this means that in order to move from one state to another, there is a transition matrix here. So by the way, the movement can only be one-sided. It makes sense, right? So that's I mean, it doesn't make 100% sense actually, because users can actually in theory move back, but those have not been considered in this model. um, we can explore more what possibilities lie in order to take into account feedback loops, or not feedback loops, or probably reverse journeys of things. But for now, it's a one-sided journey that we're considering. So that's why all the arrows are directed unidirectionally. So by the way, some of so this part of it, the calculation part of it, this is a very common example, but I just taken the liberty of using this from an existing Medium article, a very nice article. So I'll share that in the description, the YouTube description. So please go through that. I certainly want to assign credit to the rightful person who generated this part, but yeah, really good stuff. So let's look at the total probability of conversion now. So we have the transition probabilities within the different channels, right? So we can now calculate the total probability. So suppose the user is going through this one. So from start to C1, then it goes to C2, then C3, and then it finally converts. So what is the probability of conversion? This one, right? And then you have the user starting from here, and then it goes to C3 and then converts. So it's given by this. So what's the probability here? So these states are considered, so the dependence is only on the previous state. So that's why, when you say that it's probability of going from C1 to C2 is easily given by 0.5, this one here. So by the way, there's also the 50% probability of getting started with C1 in the first place, so you have to multiply that as well. So 0.5 into 0.5, 0.5 into 0.5 into 1 into 0.6, right? So that's it. So this path here, this one here, that's 0.15. Similarly, the other one is 0.3, and you have a 45%, a 0.45 probability of conversion, right? So we have to so that the probability of conversion for this entire user's journey is 45%, considering all the possible paths. Now let's assume that we have to calculate the contribution of channel C1, so we can individually calculate the contribution of each channel. That's what we want eventually, right? I mean, just having overall probability is not enough. So in order to get to that, we'll remove channel C1 from the model and see how many conversions are happening without C1 in the picture. Okay, so we're going to remove C1, and so this is where we come to the concept of removal effect. So what's going to be the effect of removal of a particular channel? So now it becomes null. Everything else remains the same, and now the probabilities, the transition probabilities remain the same. Now let's redo the calculation. So what's the probability of conversion after removing C1? Means that now it can no longer go there, right? I mean that doesn't exist. So the user has to go through this path here. So C2, C3 convert. That's the only path, and we have seen that it's zero point 0.5 into 1 into 0.06, and that's zero point 0.3, right? So we had that calculation before as well. So it's zero point 0.3, so 30%. So the drop here, that so from 30%, from 45% to 30% now. So 30% customer interactions can now be converted without channel C1 in the first place. So you're assigning that remaining one. So the removal effect is basically zero point 0.3 by zero point 0.5. So saying that the ratio, you can say, is essentially the removal effect. Similarly, you can actually do the calculation C2 and C3 as well, and see that if you remove C3 and C2, it's going to be 100%. I leave that as an assignment to you, like as to why. So if you actually remove these two channels, you're going to have 100% removal effect, because you will find out that there's actually no way a user can convert without these, either of these channels can being present. So now we have talked about this method. Let's actually talk about the limitations of Markov chain attribution. So hope this was clear, by the way. So you can understand each channel's attribution contribution in this fashion by using the concept of transition probabilities, number one, and number two, removal effects. As simple as that. So now comes the question of, what are the limitations? Are we going to use it always? Are there challenges? Of course. So first of all, the memoryless assumption. So it's a Markov property, which means that the model depends on the concept that the next channel only depends on the current one. I've already mentioned that, and so that's the concept of memoryless, because it doesn't care what happened in the past. It doesn't know what happened in the past in its model, so it doesn't even consider that. So that's problematic, right? Um, so yeah, in reality, customer behavior will depend on all these steps, not just the most recent one, right? So for instance, someone saw both Facebook ad and an email. So it might, their response might differ from someone who only saw email. All right. So it also assumes stationarity. So meaning that its transition probabilities are assumed to be constant over time. The transition probabilities between different channels, for instance, every pair of channel. So that's also possibly going to change, like user behavior shifts with seasonality, campaign timing, ad fatigue. Very, very good points, right? I mean, so for instance, when you're moving from this channel to this channel, say for instance, if I go back to the original one, so from C1 to C2, is it necessary that every user after going to C1, they always will have a 50% chance of moving on to channel 2? Maybe not. Maybe sometimes it could become 70%, right? So suppose they see an ad on Google, or rather they see an ad on Facebook. Is there 50% chance that they will go to Google after that? How do we know that? Like, we can theorize, we can model it, but it can vary, right? So there's going to be variability. So no attribution to offline or external factors, doesn't account for user level context, right? I mean, it treats all users as the same, because that's the problem. But there can be high value users, loyal customers. Personalization or segmentation is by user type is not built in. So there's no such hyper focusing or hyper segmenting by customer, the level, the type of users. Fragmentation and data sparsity, so it can lead to incomplete transitions. If channel appears too few paths, removal effect might be statistically unstable. The conversion probability is not equal to revenue impact. Okay, so it assigns credit based on conversion rates and not revenue, because we are talking about the transition probabilities, right? So that's a problem, because a channel may drive small sales. It may look more valuable than one which is actually driving fewer but more higher value conversions, right? So this might have already occurred to you. I mean, must have. So it doesn't optimize for LTV, for instance. Again, there can be like modified versions, so one can always conceptualize that. I mean, even as I'm discussing this in this video, some ideas are coming to mind how we can actually have like an augmented Markov concepts. But yeah, I mean, in general, in its essence, these are some of the limitations. So there can be some other limitations like complex implementation and causal inference. Well, yeah, it's doubtful whether it can be called a very causally powerful model, because just removing a channel doesn't really reduce conversions, because and it reduces conversions doesn't necessarily mean that it causes conversions. Um, but then again, in incrementality testing, a very similar concept is actually used, right? So it's actually used, the idea that if you are not holding, if you're withholding, showing an ad from a particular geo, for instance, and you see a drop in geo, so that's a proportional loss in conversions because of that effect. So you can often, that's often considered as a treatment effect. But the problem um, is that in this case, like there are some constraints. There's an experimental setup there. Even if it's a quasi experimental, like there are some guardrails, but there are no such guardrails here. You just remove a model here in the Markov chain concept. Again, there can be augmentations to it. So yeah, I mean, that is the whole idea. I have provided a sample code here. This will give you a simulated approach to generating the removal effects, the attribution scores, as you can see here. So you can take a look. This guide will be available, this guide doc as well. So I hope that was clear. That is the overall idea for Markov chain attribution model. This is one method for doing a custom attribution model. There can be many approaches. Sometimes I think if you might have to come up with a model on your own just by looking at the data, but it must be mathematically consistent, and you should not it should not be like just a wild idea which doesn't have a mathematical basis. So if you have any questions, just leave them in the comments below. Happy to have those conversations. And yeah, thanks for watching. I'll come back with more future iterations on this, like a more detailed explanation on the interpretation. And thanks for watching again. And till next time, take care.